Welcome. This is new lesson, integral functions. So in this lesson, we will learn about infinite series solution. What we did before, that was called a closed form solution. A closed form solution means that we can get a solution where, for example, can be represented by elementary functions such as polynomial, trigonometric functions, logarithmic function, and so on and so forth. Uh, Infinite series solution, we cannot be represented by this elementary function in an infinite elementary function, but it has to be presented like there is a solution, like my integral has a solution, an analytical solution, but it is not in the form of polynomials or trigonometric functions, finite, but infinite series. Okay, and that's what we will learn today. So you will understand the fundamental of integral functions. So that's called like integral function, and then we will apply this integral function to basic engineering problem. Okay, so integrations that cannot be presented by closed form solution can be presented by infinite series. Uh, so the infinite series, these approximate value through summation or integral process. So like you get an approximate value through a series. And we've seen some of these series before. Remember, like we've seen the Taylor series, we've seen the Maclaurin series, there's Power series, there is Fourier series, Maclaurin series. If you remember, that's a special case of Taylor series, where Taylor series, if you remember, we can represent a function by its derivative, approximative function by its derivative, and Maclaurin series, that is a special case of this. There's Power series, there's Fourier series, where you can express a function by sine and cosine. So for example, like if you remember me, just you remember something like this, the Maclaurin series, we had like e to the power x could be not equal, but approximately equal to 1 factorial of 1x plus factorial of 2x plus something like this. Yeah, you remember we did this in we did this in the differential calculus module. If you go back, you can check this. So this Maclaurin series and this is a special case of Taylor series. So basically what we are doing here, we are approximating this function, yeah, this exponential function by a series, yeah, and the more series you include, the more solution. So as this goes to infinity, that will be like the exact solution or something like this. Yeah. What are other so integral function? Yeah. There are like several integral functions. Yeah, and let me show you. And these integral function, they have an infinite series solution. So example of this integral function, for example, is something called like exponential function. That's called like exponential function. That's an example of an integral function. So integral x. Another example is error function. So error function of x. We will look at this when we get into the modeling part and the analytical solution for contaminant transport equation. We will get it in terms of error function. Other like gamma function, for example, gamma function. That's like another uh, example of integral function. Euler constant, which is equal to something like this. So these are example of integral function, yeah, and these usually when we have, for example, like in your problem in your mathematical model, like it has like a complex form or it has a complex boundary that cannot be represented by elementary function like polynomial, trigonometric function, we can solve integral function by either infinite series or even numerically. Okay, so for example, let me just show you an example. So I will show you one example here, exponential function, and then this could be later, like in the modeling module, I will show you like the error function. But let me show you like this one, like the exponential function. So this is like, I will show you like integral exponential function. Yeah. Uh, explain the regular function. So that's basically how the function looks like. So it's a function of x, u, whatever, and then you can express it in this way, like you integrate from x to infinity, e to the power minus. Here, this is like a dummy variable. I can put it, let me put it like psi, for example. Yeah. This is just a dummy variable that will disappear after the integration. So this is just for the integration part. Yeah. And then here psi, for example, and here. So this is an example of this is called integral exponential function. This function has an analytical solution, but it's not a closed form. It's not like, remember, like this, for example, like x to the power 3 times 4. This integral. That's equal to what? That is equal to x to the power 4 times 4 divided by 4. That's equal x to the power 4 plus c. This is called like a closed form solution. This guy, if I did this integration, I'm not going to get a polynomial or a trigonometric function like this. I will get an infinite series solution. So basically, like for this guy, what I will get, like the solution of this guy, it has an analytical solution. The solution looks something like this. It will be like negative CE, that's like the Euler constant, okay, minus ln x, yeah, that's minus ln x, minus negative from n equal to 1 to infinity, negative 1 to the power n, x to the power n, and then n. That's the solution of this guy. So you see this guy, like this integral function here, it has an analytical solution, but it's not a closed form solution. It's not something that looks like this, yeah? It's not something that looks like this. It is something, this is an infinite series, because you see here, this is an infinite series. This is an infinite series. Okay, but why this is useful? Like, why do we need to learn? I already told you why this guy is useful. Because, for example, like the advection dispersion equation for contaminant transport. It has an for some forms of it has analytical solution. Some forms of it does not have analytical solution, and you have to solve it numerically. But some forms of it has analytical solution, and the analytical solution you can use error function. Uh, I will show you an example in water resources engineering when you have a well and you're pumping water. So you can pump this water for municipal, industrial, irrigation use or whatever. And this equation, you need, it has like the form of exponential function, and you need to solve it using an infinite series solution. So the solution looks something like this basically. Uh, so let's look at this problem. I have this problem here for you. Yeah. So I have the problem here for you. Let me just put this guy here. Let me move this guy here. So let me maybe explain like the physics of the problem first. Maybe a little bit bigger here. Let me bring this a little bit inside here. Bring this a little bit inside here. Yeah. Let's see how we are doing in time. We're doing good. Okay, so let me explain a little bit. So this is like an unconfined aquifer where you have a confining layer here. Here, oh, sorry. This is like an unconfined aquifer. Yeah, this is a confining layer. This is an unconfined aquifer. Here you have a pumping well. This is where you are pumping water out for irrigation, municipal use, industrial use, whatever. And this is where you have an observation well. Here, this is a hydraulic head. So this is the hydraulic head before pumping. So before you pump, this would be like, we just assume it's like constant. And then after you pump, what you expect, like your hydraulic head will drop, like pressure will drop here. You expect like your hydraulic head will drop here. And the further you go away from pumping, you'll have like less drawdown. So drawdown basically is S. So the drawdown, like this guy S here, that is your original hydraulic head minus the head after pumping. So here, that's like the maximum drawdown will occur here, for example. Yeah. So that is the maximum drawdown where you are pumping. Here, as you keep going, like if you here approach infinity, the drawdown will, like as x approaches infinity, like you go in the x direction, the drawdown will approach zero. Like there will be like as you just go far away, then you'll have no drawdown. Yeah, that makes sense. Yeah, head will not drop. It drop most close to here and far away from here. This is R, like how far you are. So here, like as R approaches like infinity, S approaches zero. Drawdown is zero, and as R approaches zero, like this is the maximum. Yeah, that's where you get the maximum drawdown. Okay. And then here is, this is the head, like your hydraulic head. This is RQ. This is how much I'm pumping. So this is Q. This will have the unit of volume over time, like L cube over T. This R here will have a unit of length. H here will have a unit of length. Drawdown here will have like a unit of length. Yeah. Okay, so that is basically is the physics of the problem. But actually, I can express this drawdown. I can express. I'm not going to show you the derivation of this because this is not a groundwater hydrology class. I just show you that I can express this drawdown actually as Q over 4 pi T. T is the transmissivity. So transmissivity is like hydraulic conductivity times the aquifer thickness. So this is B. Hydraulic conductivity times B, that's like transmissivity. We've seen hydraulic conductivity before. This has length over time. Aquifer thickness, this has length. So transmissivity unit will be a length square over time, for example. Yeah. That's transmissivity. But again, this is not important. And then time what? Exponential integral function. So u to infinity, okay, e to the power. Let me just, this is psi, this is just like dummy for integrations. It's called like an integration now. Yeah. Okay, so basically it looks something like this. Yeah, where u, like u, is giving as r, okay, and r square. So r, that is like the distance here. S, storativity, aquifer storativity, basically like telling you about the storativity, like the water storage, over 4t, and this is time. So time since pumping. So because this is also a function of time, yeah. Because the more I pump, the more this level will go down. So, and that's a function of storativity, and that's the function of the transmissivity of the aquifer. So how much the storage and how much release from storage, like the aquifer potential for release of storage and to transmit water plus time, that will give you your U. But that's not important. This like the most important part here is like this guy. So now I can express this drawdown with then like this constant here time my integral exponential integral function. So what do we do here? Can we solve this guy? Yes, we can solve this guy because we know that this guy has a solution. Yeah, I know that this guy, let me get rid of these things. I have more space here. So I know that this guy has a solution. Yes, this guy here has a solution. So the solution of this guy, like e I function of u or x or whatever, that is equal to psi over psi e psi. And what is the solution of this guy? That is negative, my Euler constant, negative len x. Get rid of this guy. Negative len x, negative to the power infinity, and is equal to 1, negative 1, and yeah, and that would be like this is negative 1, n u to the power of n divided by n to the power of n minus 1. Wow. So now I solve this. So now this equation, actually I can solve it because I can just replace this guy here with this guy here. So I just like replace this guy with this guy. Yeah. Just put this guy here. Yeah. I just put like this guy here, and then I have a solution. Yeah. So I mean, let me show you like this one. Like let me, so this guy here. Let me put more like Euler constant. I know Euler constant is negative 0.05772 minus len u. Here, this is, sorry, this is u here, because this is a function of u, so this is u. Len u, yeah, plus, now I can expand this guy, so let me just expand this guy. So that is like negative here, and I have 1 to the negative 1, so that's like negative 1, and then I have u to the power 1 divided by n, which is 1 times 1 factorial. So this will give me this, like go away, like this go away, this go away, this negative go away with this negative, so I got like plus u here. Let me do this for the second term. So the second term, this is to the power of 2, so I get negative, this negative 1, like this is to the power of 2, this negative 1 become positive, time negative, so I have like a negative here. yeah, and then u to the power 2 time 2 to, yeah, something like this. And then you can expect what will come next. So what will come next would be positive, yeah? So that here I'll have positive, that would be like u3, and then you can expect what will come next, yeah? That would be u4, yeah? And this will just go on and on and on, yeah? So now I can actually, I have u, so I can evaluate u, substitute u here, calculate this approximate solution. Again, this is not a closed form solution. This is just an integral function. And approximate solutions, the solution will be more accurate by considering more terms. So here I'm considering how many terms like I'm considering here. I'm considering like up to like u to the power of 4. Yeah. So I'm considering up to like u to the power of 4. Like if I consider more terms, then I will get more accurate solution. Yeah. Okay. So basically, I have something like this, and basically I can use it to solve this type of problem. So let me give you, do I have an example here? Hopefully, let me see if I have an example here. I have an example here, yeah. Okay, so uh, yeah, let's just do this example. Yeah, so I have an example here, and basically it is telling you Q is given. Yeah, so I'm giving Q, I'm giving T, I'm giving storativity. Find drawdown 1 kilometer from the well after 1 year. Okay, so now, uh, so I'm giving time, that is like 365 days, because remember here I have in day, here I have in day. So that is like after 1 year, and I'm giving R. This is in meter, so I need this 1 kilometer, so this is 1,000 meter. Yeah. So I'm giving R. So if I have this information, so again, this is my drawdown is equal to H negative H Q over 4 pi, and then this is my WU here, like, let me, this is, we call this WU like the well function. So in groundwater terminology, sorry, this is a big U. In groundwater terminology, this exponential integral function, this is called, like in mathematics, this is called exponential integral function. In groundwater, we call this like well function. Yeah. Integral. Here's a integral. Ex exponential integral function, we call it like so. That's the same thing, yeah. So can we solve this problem? Yes, we can solve this problem. So the first step to do, like when you get, like, you can evaluate the u, yeah. So we can evaluate the u. So the u is equal to r square, that is 1,000. And let me put the unit here just to make sure that the dimensions are matching, yeah. So we got like this is square, yeah, time s, this is dimensionless, yeah, 10 to the power minus 4 over 4, I think this is a mistake here. This is not pi, this is 4. Did I have this mistake previously also? I didn't show this equation. Oh, I sure this is the equation. Yeah, this is correct. Yeah, 4t. Yeah. Here, this is a typo here. This is no pi here. This is for t transmissivity time. Yeah, so this is 4 time transmissivity is giving by this guy 600 meter cube per day, and we are giving 365 day. So what do we get here? The unit. So the unit here, we got like this guy, yeah, will go away with this guy, and this guy will go away with this guy, so we get something that's unitless. Okay, so if you evaluated this, the number that I got, like if I did this correctly, I got like 5.566 10 to the power minus 4. Okay, let me delete this. Okay, so I got this guy here. U is equal to this U. Now, I'm asking you to find S. So S is equal to Q over 4 T T W U. And do I know this guy? Yes, I know this guy. So I know like this guy is equal to, I have a solution for this, not equal, approximately equal. I'll just write the solution, yeah? That's like my, oh, I think I have a mistake. I think I did, that's correct. I didn't do a mistake here. That's equal to negative, yeah? Or maybe I did a mistake. Did I do a mistake here? No, that's correct. So I didn't do any mistake. So that's my Euler number, negative 5.772 minus ln u minus plus u plus minus u to plus. Okay, so I know that this guy is approximately equal to something like this, yeah? So what do? Like you just substitute the u here, you substitute the u here, you substitute this u here, you substitute this u here. This is len u, this is u, this is like square, this is cube. And if you evaluated this guy, that will give you 7.115. Yeah. Okay, so now I solved the problem actually. Now I can know after 1 year at a distance of 1 kilometer how much drawdown, like how much the uh, hydraulic had dropped. Yeah. So that is, so S is equal to, uh, again, let me write it down. S is equal to Q over 4T TWU. So Q is given, so Q is giving here 15 meter cube per day divided by 4. T is given, which is 6 600 meter cube per day. Yes, this is giving 600 meter cube per day. And T is given, which is 365 day. So we should expect like so. This day will go away with this day. This guy will go away with this guy. So we only got one of them. Yeah. This guy. And what do we have here? Oh, sorry, transmissivity is not meter cube per day. I did something wrong. Transmissivity is like meter, yeah, transmissivity is meter cube per day, yes. So the transmissivity here is just like meter cube per day, that's correct. So, and this is the day, so this guy will go away with this guy. And okay. I think this equation was correct actually. This is just like pi 4 pi time t, because 4 pi, so now I have 4 pi uh, time, no time here. So the time is only in this function here, so there's no time here. So this actually, this is correct, yeah. So this is correct. So I think I wrote, this is correct, yeah, this is correct. This is 4 pi t, yes, so this is correct, yes. I think I was just confused about this guy. So this is 4 pi t, yeah, so this is correct. So this will go away with this guy. This will, this is meter cube, yeah. So now this is now correct, yeah. So this will go away with this guy. This will go away with this guy. We got m here, like this is m cube. This will go away. You got just one here. And if you evaluated this, what you will get, so if I did, and then of course time my WU, so what's my WU? So this is 7.115. And if I evaluated this, I'll get 1.4 meter. Yeah. So you got 1.4 meter. Okay, so basically, so if you live in this area, somebody will be pumping water away from you like 1 kilometer after 1 year. If you have like a well here, let's say you have your well here, okay, you will have a pressure drop of like a head drop of about 1 meter. Yeah, so the head drop here, that would be about like 1 meter or whatever. Yeah, you, or here, yeah, or whatever. Okay, so let's see how we are doing in time. So we are doing good in time. Uh, yes, we have here, this is our solution here. So now you know infinite series solution. So this is your problem for your homework. There's no tutorial because there's not much really to do. It's like straightforward. So here, like this is your tutorial. The drawdown can be presented by this guy here, where u is given by this. The solution of this equation is can be expressed in this like exponential integral, where this is equal to this. The above solution is analytical solution closed form. It's an analytical solution, yeah, but it's not a closed form. Yeah, so this is wrong. Analytical solution, infinite series solution, yes. This is analytical solution, it's an infinite series, you see here. This is infinite series. Numerical solution, quadratic rule. No, I mean, we can solve this guy like this. This guy, this can be solved numerically, but in that case here, we're not solving it numerically. We are solving it here analytically. We are solving it here, yeah, analytically. We are not solving it numerically. We are like solving it here analytically. Uh, so this is like numerical solution, quadratic rule. No, I mean, this is not a numerical solution. Quadratic rule, this is famous way of like doing integration. numerical integration like quadratic rule, but this is not the case. Numerical solution trap rule, there is no such thing as trap rule. This is just a trap for the students who are not watching the video. Yeah. Okay. Uh, and here I am giving you this problem just to solve simple like stuff. Basically, I just want to make sure. So the drawdown can be presented by this. The solution of the equation is this, where E, this is the infinite series solution. By considering only the first four term of the above infinite series, so the first four terms, that would be like 1, 2, 3, 4, like up to here. So you don't consider this guy, you don't consider this guy. So basically, like by uh, just considering the first four term of the above infinite series, find S, like drawdown, where T, so I'm giving you T, I'm giving you storativity like big S. Where is the big S? Like so I'm giving you, this is the storativity, which is 3 10 to the power minus 4. I'm giving you R here, which is the infinite series where T R is equal to 2 kilometer. Make sure you convert this to meters, so this would be like 2000 meter. And I'm giving you T in day, which is like 30. And I'm giving you what else, like transmissivity. So this is giving to you like 5 to the power 10 of minus 2. So this is here in meter, this is in day, this is in meter cube per day. So I'm giving you all this. You can calculate the U, and then after you calculate the U, you substitute it here and calculate like this guy here, and then you substitute this guy here. Q is given, so Q is giving, and transmissivity, which is this guy is given, you know 4 and you know pi, and then you can calculate this guy. So you can find the S, which would be, I don't know, like 1 meter, 2 meter, 3 meter, 4 meter, whatever. Yeah. So you just find this number that would be in meter. Yeah. Okay, so I think that's all for this lesson. Yeah. And I will see you in the next